Thank you very much for joining us in this last session of the second day of IMAV 2021. Now we have the control system session number 4, and we have 3 interesting papers. So we have the paper number 21, 7 and 17. So I think all presenters are here. So, okay. So the first one is the paper number 21. Christophe?
Yes, good evening.
Okay, so could you start your presentation, please?
Yes, certainly. Give me 1 second to share my screen.
Yes.
I will try to present for you the hybrid UAV attitude control. Of course, after such an interesting keynote, I hope you can still follow. And here is welcome to the presentation of the paper called Hybrid UAV Attitude Control using Incremental Nonlinear Dynamic Inversion and Dynamic Tilt Twist. The work was done by my student Lars Delleman, and I'll try to present his work as well as possible. For a long time, the research on flight control of UAV was focused on quadcopters because they are simple, cheap, and versatile. They have only 4 moving parts and therefore are a great study object. And fixed-wing aircraft because they have a very good endurance. They have a very good lift-to-drag ratio, can stay in the air with little energy and thereby achieve very long ranges and very high speeds. But recently, in the last decade, a lot of attention was given to so-called hybrid UAV. One of those hybrid aircraft is the Neder Drone. The Neder Drone was developed in Delft to be a versatile vertical takeoff and long endurance hydrogen-powered aircraft. The fuselage is shaped around a pressure cylinder with hydrogen, and in the rear and the back we have a fuel cell. It has very high aspect ratio wings for minimal drag and long endurance. And thanks to its 12 motors spread over the long wing, we have hover capabilities. So the objective of this study is to improve the accuracy of the position control of the hybrid Neder Drone for the mission of landing on, for instance, a moving vessel. And that moving vessel is typically surrounded with wind and turbulence. And one of the objectives of this study is to not need hardware modifications. It then includes running a controller on board the same autopilot with the same microcontroller, which excludes some of the most advanced control theories. The Neder Drone is now flying with incremental nonlinear dynamic inversion control. The nice properties of this type of control is it is sensor-based. You only need a good model of the controls, so a good estimation of the control effectiveness matrix, but you don't need a very accurate aerodynamic model of the whole platform, as the sensors, the accelerometers, are actually measuring the external forces on the platform. The implementation includes a linear model to create reference signals before it enters the INDI control. And the work presented in this paper is about how to create effective reference signals for hybrid UAV. This feedback system can be done either in Euler angles. It can be done in quaternions. The quaternion is basically one rotation in between 2 coordinate systems, and it's mathematically the shortest rotation. Very interesting. And but recently another suggestion came up, which is tilt twist. This one splits the pitch and roll from the yaw, as in most helicopters the thrust vectoring principle is used for position control, and that has a higher priority than setting the yaw. But when flying in quaternions, the matrix multiplications correspond to the shortest rotation in between 2 coordinate systems. If we look at this animation here, we can imagine that the red block represents a thrust vector, a current state vector, and the blue block represents a desired state. A quaternion multiplication then provides the shortest rotation to go from actual to desired state. But if these blocks were thrust vectors, this does not correspond to the shortest rotation between the thrust vectors, which would be a rotation in the red and blue plane. And you can see right now that the yellow block, so in between states, has a very big lateral offset. If we are thereby interested in position control, and the thrust vector is what determines how the position is steered, having these lateral offsets is not desirable at all. When does this happen? It happens in two cases. First of all, only when there are large errors, with tiny errors in the orders of a 1 degree roll and 1 degree pitch, the difference will be almost invisible. And the other part is, if not all three rotations can be executed at the same speed or at the same rate with the same response time, then the quaternion control runs into trouble, because the quaternion describes one rotation around one axis, but if the platform can rotate faster around one than the other axis, then it doesn't do what you expect it to do, and you end up with perturbations. In the case of the Neder Drone, which has very long wings, the roll is, for instance, much more controllable than the pitch, which has a much shorter arm, and the yaw, because of the damping of the wings, is by far the hardest to control. In such a case, tilt twist can come to the rescue. It was proposed by Beach et al. In 2014, but it has never been combined with the powerful sensor-based control of INDI. Tilt twist starts by finding the shortest rotation to get from the current tilt vector, which is typically corresponding to the thrust vector, to the desired thrust vector, and thereby effectively maximizes the response for the outer loop position control loop in helicopters. Once the tilt is corrected as quickly as possible, then we correct for twist. This method has been successfully applied on quadrotors, where the tilt is also much faster than the yaw, than the twist. Twist is done with torque of propellers and is always slower. The yaw is also less important for the position control. How does tilt twist work? Well, if we represent the current attitude with a rotation matrix RC and the desired attitude with a rotation matrix RD, then the matrix multiplication with the inverse yields the error in between both. And the last column represents a vector of which the arctangents of some elements are the tilt rotation in X and Y plane. For the twist, it's a bit more fiddly. We need to create an intermediate coordinate system called RP, which represents the attitude, what the attitude will be after correcting for the tilt error. This is done using the Rodriguez rotation formula, RV, which describes the rotation of a vector along another vector. And the twist error is then defined as the inverse cosine of the dot product between the two x-axes. What does the difference between quaternion control and tilt-twist control look like on a system with slow yaw dynamics? To investigate that, we created a Simulink model in which the yaw axis was made 10 times slower than the other axis. When you start with a large error, you can see that the pitch and roll angles, in the case of quaternion control, only start to go towards zero when the yaw angle is actually also zero. For the tilt-twist control, on the other hand, the pitch and roll angles very quickly at 0.6 seconds have reached their set point. This means the tilt vector or the thrust for a quadcopter is pointing in the correct direction, And of course, this is used in the outer loop for the position control. In other words, this simulation shows that with normal quaternion control, as long as your yaw angle is not reaching the desired value, then your pitch and roll are disturbed. And for some platforms, that's particularly important. For instance, in the Neder Drone with very long wings, which can catch wind, this effect shows up very hard. But Tilt Twist was designed for quadcopters or all platforms in which the lift vector corresponds with the tilt vector. But tail-sitting UAV transition from hover to vertical to half transition flight, where the pitch angle changes 90 degrees. So in a pure hover without wind, the lift vector would be in the Z direction. But whenever there's a lot of wind, the total lift vector and thrust vector will be in the X axis. To address this, dynamic tilt twist was introduced, which states that not the tilt axis should be performing the shortest rotation, but the lift axis. And by introducing a rotation matrix with the transition angle, we can achieve that. The total formula for dynamic tilt twist comprises of a simple correction for the transition angle before performing the same tilt twist algorithm as shown before. And the feedback error then needs to be reconverted after having had its lower gain, so that there's time separation between tilt and twist. To address this, we made a simulator with a more complete model of the drone, the Neder Drone, and had it fly between 2 points back and forth. But during the flight, large jumps in set point were introduced, errors which the drone could never track, errors way beyond its capabilities. In the bottom plot, you see that the desired set point has abrupt changes to simulate what would happen in case the wind would pull on a wing or turbulence would destabilize temporarily the yaw of the Neder Drone. And then seeing how the rest of the position control holds up. The result looks like this. We compared quaternion control in the first plot with normal tilt twist and with dynamic tilt twist, 3 controllers. The simulation included a model that was not perfectly tuned, but nevertheless you can clearly see that the quaternion control yields much less repetitive patterns, and that the one that's most aligned with the desired direction is the dynamic tilt twist control. The exact same algorithm was then tested on the real Neder Drone. Here we see a takeoff. It's a so-called angled takeoff. And here's the start of the test. The first part, we have this aggressive 45-degree heading angle changes, while at the same time it's trying to precisely track a line from A to B, back and forth. Here's another aggressive yaw change, and that results in at least over a second where the drone cannot precisely follow the yaw command, and during that time it goes away from its desired set point. With tilt twist control, depending on the wind conditions, for instance, if there's no wind, tilt twist control, where the drone will be perfectly vertical and where the lift will be in the direction of the tilt, yields great results. For this test, we awaited much more wind, where you can see that the drone is at about 50 degrees nose down attitude, which already yields quite some couplings. And finally, when we enable the dynamic tilt twist, we see that the drone moves a bit more, so it compensates faster. But the final goal, the desire from the beginning, is to stay more precisely on the line and not put too much importance on the yaw, is perfectly achieved. The final phase of the flight is a manual landing. So you can see the weather was not so great. It was actually raining. And without wind, we're close to the ground. In the ground effect, the drone is almost nose up. Let's have a look at the same flight plotted in graphs. The first part is again the Quaternion control. The relative wind direction is indicated with the arrow, so it had a phase where it was actually facing the wind much more and a bit flatter, and a part where it was going backward. We again see, just like in simulation, that the Quaternion control has much worse position control and is further off the desired path, which is indicated by the red line. Tilt twist control does a lot better, and as I said, without wind, it actually does very well. But the dynamic tilt twist is closest to the desired line in this flight. Expressed in numbers, so the distance between the current instantaneous position and the desired position was an average of 3.27 meters for the Quaternion control, 2.7 for the tilt twist, and 2.08 for the dynamic tilt twist. Conclusions. Quaternions give the shortest rotation between the attitude and the set point. It's a mathematical formula which is there's no shorter rotation. But if you have very large set point errors and you have differences in response speed for the three axes, which is definitely the case for transitioning hybrid UAV, then it does not give the optimal solution, as the thrust factor is not doing the shortest rotation. Tilt twist, on the other hand, does give the shortest rotation of the tilt factor, but in hybrid and transitioning aircraft, this does not always align with the direction of lift, and thereby it's a great method for quadcopters and helicopters, but has shortcomings in transitioning aircraft, like the Neder Drone. The dynamic tilt twist gives the shortest rotation of the lift factor, even on a transitioning UAV. To combine this powerful tilt twist ID with a powerful controller as INDI gave very interesting results. To our knowledge, this is the first time that INDI and tilt twist was combined. And the proposed dynamic tilt twist also yields the shortest rotation of the lift factor independent of the transition angle on the platform. And from flight tests, we could see that this helps in reaching the smallest position error. For precision flying and landing, this is the most important metric. Flight tests were performed on the Neder Drone and yielded a clear improvement. This was our presentation of hybrid UAV attitude control using INDI and dynamic tilt twist. Thank you for your attention, and if there are any questions, we'll gladly try to address them. Welcome to the presentation of the paper called.
Okay, so thank you, Christoph, for this interesting presentation. It's very exciting to see this experimental test. So maybe we have time for one question. There are the question? No? Are you here, Christoph?
Yes, I'm here.
Okay, so I have one question. For example, in the case of the Quaternion control, I think that you are using the vectorial part of the Quaternion error. Okay, so do you use the same gains for the three components?
Thank you for the question. It's a very interesting part of the theory. So Quaternion represents in body axis rotations around three axes, and when you can react at the same rate around all axes, then there's no problem.
But in a lot of platforms, the actuators have different response speeds and also different, sometimes even different deflections. And so that means that if the actuator is different, then you will also have another gain. What some people have done is to choose the gains in such a way that the turn rate in all three axes becomes similar, which actually can only mean one thing, is that you slow down the faster to match the slowest. And that is, in terms of position control, also not very elegant, because the platform could be faster. I hope this addresses your question.
Okay. Yeah, because maybe if you can use different gain in each component of the quaternion error, or even maybe you can use the saturation function. Maybe you can regulate the speed of convergence of each X. So, but maybe, maybe it's only a suggestion.
Yes, you can definitely do that. You can make it react along the desired rotation that the quaternion describes. And the solution to do that is to slow down the fastest axis to the speed of the slowest, so that then you can guarantee that the rotation is along the desired axis. So we do use different gains on all axes, but chose an approach which maximizes the use of the fast responses in order to get better position.
Yeah. Okay, I agree. Okay, so thank you very much for your response. Thank you for your presentation. Okay, so we continue. The next paper is the paper number 7. Are you here? Yeah, the author of paper number 7 is here.
Yeah, here.
Ivan, okay, Ivan Martinez.
Yeah.
Okay, Ivan, so you have 15 minutes for present your work.
Right, yeah. Can you see the presentation?
Yes, yes, we can see.
Okay, so well, hello everyone. Welcome to the 12th International Micro Vehicle Conference and Competition. My name is Ivan Martinez Perez, and then I'm going to present the article called Sliding Mode-Based Truth Vector Control for aircrafts. Part of the contents of this presentation, we have a brief introduction, followed by the rocket dynamic model, made up of translational dynamics, rotational and translational kinematics, and finally the proposed control design and conclusions. In recent years, the research to achieve reusable spaceflight has been a very active area. So we focus our attention on propulsion systems that include truth vector control, TVC, which allow us to change the flight path to follow a desired path. In this article, we propose an attitude about the experimental rockets using TVC, where the equation of pitch attitude and inertial z-axis trip position are obtained. Basically, 2D. So assuming that some parameters of the aircraft are known and the airspeed is uncertain, we make it a goal to guarantee the convergence of the pitch angle and the drift position using a sliding mode-based truth vector control. Finally, some simulation results are present to show the performance of the proposed controller under different conditions. The main assumption to carry out this work was that the rocket is considered rigid, without flexibility, constant mass, with approximate aerodynamic coefficients. And considering only a single engine and therefore a single nozzle for control, the geometry of the air is considered as the ellipsoid proposed by the World Geodesic System in 1984. The position of the rocket is defined by the Earth Central Inertial Reference Frame, while the orientation is defined by the reference frame of the body or rocket frame. Well, starting with the modeling of the rocket dynamics, we have that is defined firstly by the translational dynamics to obtain the position of the rocket at each instant of time, which is defined from Newton's second law, where it's necessary to know all the forces acting on the rocket, which are thrust force, aerodynamic force, made of lift and drag, and finally the gravity force. Thus, we obtained equation 2.5. Well, so defining each of these forces, we have the first of them, the thrust force. As we see in equation 2.2, where is the represents the total thrust force. As well as we see in figure 2, taking only the components by means of triangle relationships, we obtain the thrust vector control. In figure 3, we observe the angles delta theta and delta psi that represents the 2 degrees of freedom of movement of our nozzle. Finally, we obtain the equation 2.3. Now moving on to aerodynamic forces, we have the lift and drag, where for simple geometries, as the rocket, we can use the component of the normal force M, as we see in figure 4, and the axial force A. Now changing plane, in figure 5, we can see the third of them, the lateral slip force, which in figure 4 will normal to the plane. And thus we obtain equation 2.4. Now for more real condition, we know that the rocket in flight tends to have a small deviation known as track, where the angle formed by it and the actual trajectory is known as drift. So as we see in figure 6, the vector V represents the track, and the angle formed by it and the z-axis is the angle of drift by gamma, the letter gamma. So we have this same peculiarity in the figure 7. So defining each of these angle, the angle of attack as alpha and the angle of lateral slip beta. Firstly, we have the orientation angle, the drift angle, and finally the Duisberg angle of the air disturbances. So redefining the last equation, the equation of the aerodynamic forces by S and N about the forces, we obtain the equation 2.7. Well, now as the last force, we have the force of gravity, whereby using the ellipse of WGS 84 for a better approximation of the geometry of the air, a better approximation of gravity is obtained. It should be noted that this model is by the geocentric inertial coordinates, so it is necessary to make a transformation. Thus, we obtain equation 2.8 about the gravity force. Finally, the translational dynamics considering the aerodynamic force in conjunction with the disturbance, the thrust force defined by the thrust vector control, and finally the force of gravity considering the geometry of the air as the ellipsoid WGS 84, we have as result equation 2.9. So now to obtain the rotation of the rocket, the rotational kinematics is defined, which are still applied in aircrafts. We make use of the Euler angles, yaw, pitch, and rho. Then this rotational kinematics with respect to the SE frame, reference frame, is described as in equation 2.10, which depends of the angular velocity. Now, to obtain the rotational dynamics from Euler's second law for a rigid solid in rotation, it tells us that the sum of moments is equal to the derivative of the angular momentum, where in turn this is equal to the moment of inertia times the angular velocity. Then we obtain the equation 2.11, where it's necessary to define the rocket moments, which are the aerodynamic moment and the thrust moment, as we see in equation 2.12. And the aerodynamic moment is defined by the distance from center of gravity to the center of pressure times this force, as in equation 2.13. And the moment of thrust is defined by the distance from the center of gravity to the engine gimbal joint, as in equation 2.14. Finally, we define equation 2.15 that describes the principal moments of the rocket, where finally, by substituting this equation, we obtain the equation 2.16. Well, as a result, we have that the rocket dynamic model has 9 degrees of freedom according to the design equation that are needed to define it, with 2 being the maximum order of the rocket, of the system. Sorry. Finally, the main difference between this model and the others is the consideration of the TBC for a single nozzle and the aerodynamic disturbance. Now, starting from the mathematical model developed, assuming that the depth in the y-axis doesn't exist and taking only the xz plane and not considering the movement in x, we have that the angle phi and c are 0, as well as the angle and lateral elliptic force. In addition, that the delta epsilon nozzle angle are given by the thrust vector control. Likewise, the cy and xy planes and their combination don't exist. And finally, considering that the rocket performance angles and the TBC are small, we say that the cosine of the angle is equal to 1 and the sine of the angle is equal to the same angle. In this way, we obtain as a result the system with movement in 2D as in equation 3.1 and 3.2. Returning to the previous model and writing it as in equation 3.3, where fx represents the matrix of the system, gx the control vector, x represents the state of the system, where c and c dot represent the height, and theta dot represent the orientation. Finally, the control input is delta theta with respect to the thrust vector control. The control law is then proposed as defined in equation 3.4, where the surface S1 is defined as x1 plus x4, and G2 and KD as feedback gains. Now, taking the following proposition, considering the law of the previous equation 3.4 to control the flight path, height, and pitch angle in a rocket, then the convergence to the origin is assured infinite time if KD is large enough for any practical conditions. Then, by means of a stability proof, we aim to check the condition of the sliding mode, that is that the surface tends to 0, choosing a sufficiently large gain. This implies that according to the theory of sliding modes, it is possible convergence infinite time to the surface S from an initial condition. Then, when S is equal to 0, the trivial solution is that x1 and x4 are equal to 0. That is, z and theta dot tend to 0. This considering physical that the rocket is in an initial condition far from the origin in flight, and we want to land or reach a desired point. The following table shows the parameters for the numerical simulations. And now we can see the results, where the simulation objective is that C and theta tend to the origin given an initial condition. As we see in figure 10a, the control is able to bring to the origin as the desired state, And in figure 10b, the controller stabilizes, and finally the angle of drift and the angle of attack in the remaining figures also tend to the origin. Now, starting from this same simulation, adding the aerodynamic disturbance, we have two cases with the intention of checking the robustness of the controller considering their parametric functions. Then in the first case, we have the disturbance is considered a sinusoidal function, where its behavior is shown in figure 11a. However, despite this noise, the control is robust enough to bring the rocket to the desired state. In the second case, being more rigorous, we propose the disturbance as a Gaussian function, as we see in figure 12a. It is of higher frequency, and as expected, the controller complies with the desired robustness. Finally, as a piecework bonus to this presentation, a preliminary experimental result on the rocket is presented in order to control an experimental rocket by TVC as a part of my master thesis in aerospace engineering in Universidad Politécnica Metropolitana de Hidalgo, México. The experimental rocket is characterized by having two angles of freedom with a servo for each one, and the propulsion is carried out by means of compressor pump. In figure 12, the horizontal movement is shown, while in figure 13, the vertical movement. Finally, the figure 4 shows the stabilization test. Well, so the conclusions of this work are the following. A complete dynamic model of the experimental rocket using a TVC is presented. The angle of attack control, which allows to reduce the drift in flight through TVC, is proposed using a reduced dynamic of the rocket, 2D. A reduced dynamic of the rocket is proposed to control the angle of attack, which allows us to reduce the drift in flight through TVC. And finally, a model-free sliding mode-based TVC is presented to guarantee robustness in the presence of parametric uncertainties. So this is the main reference to this work, and thank you for your attention.
Okay. Thank you, Ivan, for this exciting presentation and for this exciting work. I see that there are many theoretical aspects here. We have time for one question. Are there questions of the audience? We can set me question here in the chat if you want. Okay, in the meantime, Ivan, the classical question is, why do you choose the slide mode control for your work?
Can you repeat it again, please?
Why do you choose the slide mode control for this work? Why not PD control or another approach?
Yeah. Well, we are focusing on the air disturbances. We realize some other proofs about other controls, like you said, PD or the linear quadratic regulator, some like that. But we couldn't control the system. So technically, it's about the response that we obtain. So in this particular work, we can Yeah, we can control the system only with this backstating slide mode controller. So that's the reason.
Okay, I think also the reject of disturbance is an objective in your work, no?
Yep.
So I think the slide mode control has many beneficial contribution in order to reject the disturbance. So maybe this is the main reason. Okay, so thank you, Ivan, for this presentation.
Yep.
Okay, so we continue. The last paper is Quaternion-based attitude slide mode control with disturbance rejection observer for a quadrotor. And the paper is the number 17. So the presenter for paper 17 is here. Juan?
Yes.
Okay. Okay, so please, Juan.
Okay, I will share the presentation.
I can see your presentation. Juan,
Sí. Yes.
You can. It's a video, no?
Yeah, it's a video.
The volume is very slow.
Oh, okay. I will.
It's very low. Maybe.
Okay. I don't know. Okay, I will present the presentation live to avoid this problem. So
If not, we can put we can play the video. Okay, so maybe Oyuki, you can play the video, Oyuki, please, because it's necessary to perform any tricks for that, I think.
okay, I continue with the video or
no? Wait a minute, please.
Okay.
You can stop sharing your screen. We are going to play your video.
Repeat, please.
Could you stop sharing your screen?
Okay, yeah.
So, because we are going to play your video, no worries. So Oyuki, please.
Okay.
When you are ready.
Yeah.
And then at the end of the video, we can have the questions and you can answer. Okay, there we go.
Okay, thank you.
There is no sound, Oyuki.
The video was recording with a very low sound.
Is there any sound with the video, Oyuki? Or can you fast forward to see whether there is any audio?
Yeah, it's only the audio. So I
It's only the video. No, there is no audio.
no. Yes, they have audio, but it's very slowly.
Very low.
Very low. Sorry.
Mhm.
So continue the video or stop the sharing.
Well, Juan, you can press in live.
Yes.
Okay, so we can switch.
Yeah, let's
Sure.
go for it, please.
Yeah. Okay. Mm, 1 minute, please.
No worries.
Okay, can you see the presentation?
Yes, we can see.
Okay, I will start. Sorry by the issues. Yes. Okay. Okay. Our work is called Quaternion based attitude sliding mode control with a disturbance rejection observer for a quadrotor. And we are Juan Ayala, Rogerio Enriquez, and Fermi Guerrero. The content of this presentation is as follows. First, I will give you an introduction. Then I will talk about the objectives of this work, followed by the methodology. Then I will show you the results. And finally, I will give you the conclusions. So the quadrotors are unmanned aerial vehicles used for multiple applications like filming, farming, vigilance, light shows, or transportation. These tasks expose the vehicles to multiple. Sorry, I have a problem. One moment, please. Okay, sorry about that. Can continue?
Yes, yes. But we can see your screen.
Okay, I will share now.
Okay.
Okay, so I was saying that the vehicles performing this task are exposed to multiple perturbations like wind gusts or environmental problems coming from other vehicles or walls. So to perform this task, a control is needed, and this is divided in 3 controllers, like the guidance controllers, where the trajectory is defined, the position controller, where the position is achieved to follow the trajectory, and the attitude controller, where the rotations of the vehicles are performed. This directly affects the position controller because the under-rotated nature of this system. In this work, we focus on the attitude controller. For the attitude of the rigid body, there are multiple representations like Euler angle, axis and angle, unitary quaternions, Rodriguez parameters, or direct cosine matrices. The unit quaternions has some advantages, like there are no singularities and only have one constraint. Also, there are a good option for faster calculations and more accurate. So the quaternions are hypercomplex numbers formed of 4 elements grouped in a scalar and a vector part. For the representation of a rotation, a unitary quaternion is needed and can be transformed to the Euler angle using this formula. Also, a quaternion can be used as a rotation operator using the quaternion product operation. A logarithm of a quaternion allows to represent the rotation in an axis and angle form using this transformation. And by the derivative of this result, we can obtain the angular velocity. The quaternion-based model of the quadrotor is writing in this form, where the G is the vehicle position, the Q is the attitude quaternion, omega is the angular velocity, K is the inertia matrix, and tau is the control torque. By applying the logarithm mapping, the quaternion model is written in this form, and we can obtain the angular velocity directly from the quaternion. In the literature, there are multiple control techniques applying in quadrotors. They're ranging from linear controllers, nonlinear controllers, to learning-based controllers. In our work, we are focused on the sliding mode control, which is a technique where the idea is to track the system to the state toward a surface called the sliding surface. Suitably chosen and design a stability controller that gives the system states on such surface. The main advantages of this technique are its fast response and good transient performance. Also, its robustness against a large class of perturbation and uncertainties. And its major disadvantages is the chattering due to high frequency switching, and this can lose on energy and a model dynamic and even actuator destruction. The sliding mode control has this general form for the first order, and the control law is formed of two terms. First, one is equivalent to the system, and the second one is nonlinear, depends of the sign of the surface. The objectives of this work are design a controller based on a slide mode technique for a quadrotor using a Quaternion-based model, and design a the state observers to improve the rejection of external perturbation and uncertainties in the model. The sliding mode control applied to the quadrotor is shown in this block diagram, where first the position control receives the reference position where the total force is obtained, and the desired angular velocity and desired quaternion are the inputs to the control, the attitude control, where the control torques are obtained, and the outputs of the system are feedback. Also, we apply some disturbances to the input control of the system and the inertia matrix to check the robustness of the control. The position control is designed from the position subsystem of the model and can write in this form, so can be treated like a linear system, and this control law is proposed. It's where she had is the position error, and from the aerodynamics we can obtain that the constants K1 and K2 must be greater than 0 to the error converge to 0 as the time tends to infinity. The design of the attitude control is from the rotational subsystem using the logarithm mapping, and defining the error quaternion, like the difference between the desired quaternion and the quaternion of the system. The desired quaternion is obtained applying some properties from the quaternion product and the logarithm and exponential operation. So, choosing a sliding surface of first order, where omega e is the angular velocity error, from the derivative of the sliding surface, we can obtain the control law for the attitude of the quadrotor. The appliance.
5 minutes. One, please.
Okay. For the observer, we can we choose to apply it to the attitude control to minimize the effects of the perturbation in this way, as this shows in this figure. So the aim of the observer is to estimate the angular velocity and the non-disturbance D. This is because the angular velocity depends directly from the uncertainties in the inertia matrix. So defining the observer in this way, where x1 hat is the angular velocity and x hat 2 is the disturbance. I will show you the simulation results in this section. So for the simulation, we choose these parameters and these design control constants. And for the trajectory of the quadrotor is an upward spiral where the quadrotor is following smoothly and with small errors. So in the same way, for the attitude control result, we see that after a brief transient of about 3 seconds, the error in the orientation is very low. So comparing the results from the sliding mode control only and with the observers, we can see that with the observer, the error is smaller, up to 10 times. The disturbances are just uniform noise added to the inertia matrix, about 20% of the nominal value. And as an external disturbances is a sine function added to the control torques. So using the EC index, we can see that the results with the observer are 3 orders of magnitude smaller than without it. Well, for conclusions, we have nonlinear sliding mode control proposed for the attitude stabilization and tracking of a quadrotor vehicle, and an extended state observer was designed to estimate the model uncertainties and improve the non-rejection and non-disturbance rejections. Finally, the results show that the observer improves the disturbance rejection up to 10 times. That's all. Thank you.
Juan, thank you very much for this presentation. Maybe we have time for one question. Is there a question? No. So only for curiosity, what is the advantage with respect the Quaternion with respect to Euler angles, Juan?
Well, as we see in the presentation, the model is simplified. Also, some singularities are avoided, and we can say the calculations are faster because of the avoid of the matrix operations and the approximation of sine and cosine functions.
Okay. Okay, so thank you very much, and thank you for your attention at this session. This was the control system session. So thank you very much, and maybe Jose